Okay, I don't know. Well, good morning, everyone. Thank you for joining us. I hope you had a good holiday weekend. Thank you so much for deciding to spend your Sunday morning attending Mithun's PhD defense. For those of you who don't know, Mithun has been a PhD student with us for about 4.5 years. Before then, he was a master's student at Ohio State. We actually met. He came to Ohio State as a master's student before I joined Ohio State. We met because he was my TA for 3260. He was looking for a master thesis project, so we started collaborating together on a project sponsored by Ford Motor Company, and something that has nothing to do with what he's going to present today. And then during his master, we decided that a PhD was actually a good idea. And so here we are, about 5 years later, 5 years after your master's thesis, something like that. A pandemic in between, everything is back on track. So fortunately, well, we stick on course. And so today we're gonna listen to Mithun's research and his results on intra-factory logistics. So his dissertation is titled Optimal Robot Fleet Selection and Resilient Management of Intra-Factory Logistics, and the project has been sponsored by Ford for the past 4 years, about 4 years. And if you're not familiar with the way these exams are held, usually we have the presentation. So as I mentioned, Mithun will present his work and his research. We will have an open forum where the audience present in the room and the online audience can ask any questions. And then we will invite the audience to leave, whether it's the Zoom meeting room or the physical room, and then we will start the exam. And that will be the closed door portion of the exam. If you have any questions during the presentation, you can type them in. I will monitor the chat. If not, I encourage you to keep the questions for the end of the presentation. And with that, Mithun, the floor is all yours.
Thank you so much.
Yes.
Thank you, Dr. Stephanie, and good morning, everyone. In the production context, multiple industrial revolutions have played a significant role in improving production efficiency, with the latest revolution, Industry 4.0, focusing on autonomous systems, particularly facilities that use robot fleets instead of assembly lines. Now, these facilities are characterized by designated regions where there are workstations for welding, joinery, and so on, and inventory locations for parts to be stored, and idling stations and charging bays where these robot fleets can idle or charge up. There are also pathways through which these robots can navigate the facility as they complete these intra-factory logistics tasks, which is basically the movement of material from one location to the other. By doing this, there has been an improvement in a lot of the production efficiency and capabilities. For one, faster product development, increase in the variety of products and mass customization, quicker deliveries to the customer, and resilience, an important factor, which is the ability to rapidly recover from disruptions. Some of the open questions in this field relate to how to optimally select this robot fleet for intra-factory logistics. This is a very costly affair because the robot fleet is expensive, and also whatever is the chosen fleet affects the operational efficiencies in the production lifecycle of the product. Methods that exist, they do not guarantee global optimality for problem sizes that are relevant to manufacturing problem. And this is a problem because this optimal fleet selection is a one-time event with a high acquisition cost. Our approach uses a combination of multiple techniques to provide the globally optimal fleet composition for a given facility requirement. The second question relates to how to coordinate this fleet once it has been acquired. So the idea is that the fleet enhances the resilience by being able to provide some flexibility in how the materials move across the facility floor. And prior approaches solve this using approximate or decentralized methods for the real-time capability, which is important in the sense of resilience. However, this does not take into account the fact that there are multiple robots that are available to solve this disruption. And to address this, our work uses a centralized fleet manager which achieves real-time capability using the transfer learning. And the third research question is how to quantify the resilience available for the facility. This is a really challenging problem because of the dimensionality of the space of variations that can cause destruction. And prior approaches, they deal with either an expert design of experiments method, where we select what might be the possible failure cases, or active learning that automates this but results in a lot of wasted queries, and they do not always reveal vulnerability. To address this, our work developed a efficient sampling algorithm that systematically identifies the boundary limits within a user-defined epsilon neighborhood. Here are the journal and conference papers that resulted from my work answering these questions, and I will now address the research questions in sequence. So let's start with the first research question, which is for a given product facility, we want to identify the robot fleet that best completes these tasks. So the inputs to the problem are the facility layout, that is the detailed information of how the different inventory locations, the workstations, etc. are located, what are the pathways, the dimension, and so on. And the material handling tasks, which is the movement of items from one location to the other with certain time periods of movement and payloads and so on. Also, there are multiple types of robots that are available for selection. So I show here an autonomous forklift, a pallet mover, a light differential drive robot, a cart puller. So these are the kinds of robots that the facility would be interested in purchasing. And we are trying to minimize some cost function which is associated with the acquisition of these robots. Because each robot has some cost for purchase and also the operating cost. So once you have a fleet, this fleet results in an operating cost with respect to how they go about completing their tasks. We're trying to minimize both of these in the cost function. And the outputs of the optimization are, of course, the fleet composition. And as I mentioned, since the fleet is responsible for that operating efficiency, we're also trying to optimize the fleet dispatch. That is how they go about in their routes and at what time do they go up and pick up items and so on. So to describe this, let us look at this simplistic layout where the gray regions, they represent inventory shelves and impassable areas such as workstations. And in this example, I'm showing 3 tasks that have to be executed. Each task has a pickup and a drop-off location marked by the ends of the arrow. And to capture this information, we use a graph representation where all the locations of interest form the vertex set. And these locations of interest are then connected to each other using these edges. And the edge represents a decision of moving from one location to the other. So for instance, if a robot chooses to go from location V1 to V2, then the binary variable relates this information. And the decision of moving from one location to the other involves a path planning that has to be conducted. And so even though it is a direct relation from V1 to V2 in this graph representation, there is a path planning that is conducted to obtain the energy and the time cost to move from one location to the other based on that facility layout. Also in our work, we capture the turning and stopping costs at intersections in addition to the usual traveling distance cost. The reason for this is because we want to capture the operational efficiencies as accurately as possible so that we don't accumulate these inefficiencies and have surprisingly high costs. All the different vertices are connected to each other to form this fully connected graph that is possibly directional depending on the graphic layout and the ability of the robot to turn efficiently and so on. Moving to the cost function, as I mentioned, there's a fleet acquisition cost. The different types of the robots, there is a cost associated with purchasing them. And the variable that's being optimized is the fleet composition vector, which is basically how many of each kind of robot we purchase. Also, there's an operational cost, which is energy in dollar equivalent, the problem that we are interested in, where the EIJ term here is the true energy to move from one location to the other, which is dependent on recharging events, where a robot might have to go to the depot to charge up if it runs out of battery and so on. And the X variable is the optimizing variable, where it decides in what sequence do these robots go from one location to the other. Now, while these robots are moving across the facility, there are many constraints that have to be respected. One, all the tasks have to be completed, of course, and the pickups must happen before the deliveries, and at each location, there's a time window within which the robot can service that location. And there are payload limits associated with each robot, so it can never carry more than its payload limit. And there are battery state of charge limits, so it should never go below the lowest possible SOC. Now, these constraints are modeled as shown, where for the first set, I show the multi-robot routing constraints. So in this, the binary variable decides how the robot moves from one location to the other, and they all start and end their tours at the depot. It is possible for some robots to not be utilized when we are exploring this fleet composition. So it's not a requirement that all robots have. And every location must be visited exactly once by a robot as it completes its duties. There are also payload and precedence constraints related to the cargo that's being carried by the robot. So they all start with an empty payload at the depot. And then there are parameters at every location. If it's a pickup, it's a positive parameter Q. And if it's a drop off, it's a negative parameter. And the relation between the pickup and corresponding drop off locations is modeled as shown here, where at the drop off, the value of the cargo being dropped off is the negative of the cargo that's being picked up. And so the constraints here also require that the Delby locations can only be visited if the corresponding pickup has already been completed. And of course, the robot payload should never exceed its capacity. Further, there are constraints on the energy consumption because we are using battery operated robots. Here, a variable Z is used to denote the state of charge of a robot. They all start from the depot fully charged. And using the path planning that is pre-computed, there is a normalized energy expense based on the battery capacity. So this normalized energy expense tells how much of that battery capacity is used to go from one location to the other. And as the robots go about their tasks, the SOC is tracked. And if the SOC is sufficient to reach that location, then it is simply the energy expense in the battery multiplied by that normalized parameter. But if it is not sufficient, then the robot has to return to the depot and there's an incurred additional cost, which is related to that movement to the depot and then the return to the location that is the target location. As a result of these charging events, there are also effects on the time taken for the robot to move from one location to the other. So the variable T captures the arrival time of a robot at some location. And this is dependent on the charging event, of course. But also every location is also assigned an earliest window at which the robot can reach and the latest window. And so the robot must arrive between these two time instances. And the operation of either picking up or dropping off an item based on the mechanism of that robot, there's an associated service time at each location. So robots are permitted to arrive earlier and then await the opening of the time window so that it can handle more diverse range of scenarios. When we consider all of these constraints with this optimization cost function, there is a very large number of interacting variables that relate to the discrete choices of both fleet composition and the routing of these robots. This results in an NP-hard problem, that is a non-deterministic polynomial time problem, where there is so far no polynomial time algorithm that can solve this problem, which scales exponentially with the size of the problem, which is in terms of what is the next location to visit, how do the robots distribute the task between themselves, and so on. As a result of this, exact algorithms, if you use them from the default settings, they do not provide optimality guarantees for larger problem sizes. And generally, the algorithm can be used de facto just for small size problems in the order of 5 to 10 locations. To address this in literature, there are meta-heuristic approaches that find approximate solutions, which it does quickly and sometimes finds near optimal solutions, but it does not provide optimality guarantees, which is of importance to us. And there are hybrid algorithms that guide these exact algorithms using the solutions from meta-heuristic approaches to enhance the convergence and likely find the globally optimal solution for large problems. There are also parallel computing approaches where the search space of possible decisions is split between the different processors, and this enhances convergence overall. And further, there are methods that decompose a problem into the constituent subproblems, which is basically the fleet composition decisions, how the tasks are assigned between the robots, and the routing decisions. Now, in this work, I combined the three methods of accelerating exact algorithms to obtain the globally optimal solution for problem sizes that are of interest to manufacturing systems. First, starting with the problem decomposition, at the highest level, we have the fleet composition optimizer, which answers the question of how many robots should form the selected fleet. This fleet composition is then sent to the task assignment level, which distributes the task between the robots of the fleet. And for a robot that's now been assigned the task, the route optimizer level looks at the sequence of visiting the locations by each robot to respect the constraints and so on. And the path planning, as I mentioned, is a pre-computed cost, which determines the energy and time taken by the robot to move between locations. And this informs the cost for the route optimizer. And the route optimizing cost provides the operating cost to the task assignment level. And the task assignment level provides the minimum cost for that candidate fleet. And in this way, we break down the problem into multiple constituent problems. And because these problems scale with the size of the problem, we are able to solve smaller problems at each level and keep the problem tractable. Now let's look at the route optimization level, where the problem is about identifying the optimal sequence of visiting these nodes. So in this example, I show two tasks, task 1 and 2, and a robot starting from the depot. It has to decide in what order does it go to these different locations. So it could go from the depot to the pickup location A, then drop off the item, then the pickup location C, then drop off the item. It could also go to the pickup locations first, so A to C, and then drop off at B to D. But if you consider the sequence A to D and C to B, it is not possible because the pickup must happen before the delivery. And so in this case, that is an invalid sequence. So the constraints are basically being considered in this level of optimization. And to address this, we use a branch and bound algorithm where we start out at the depot where no decision has been made, and then we sequentially make decisions about what is the next location to visit. Every time looking at the constraints when we decide what is a feasible next location. So let's consider here the feasible sequence A to C, B to D. From the path planning level, we get a cost of 227 maybe kilojoule. And then we look at what are the possible other solutions that could have been considered. So in this case, A to C and then D is a possibility. Here, the cost at this level is 203, which is lower than the complete solution cost found as 227. And so we can continue to explore. In this case, we find a solution cost of 214, which is lower than the previously found solution cost. So now the best solution or the incumbent solution has reduced from 227 to 214. Now we continue exploring, and if ever we find a solution, a partial solution, as shown here, A to B to C, has a partial solution cost of 215, which is higher than the lowest known cost, we no longer have to explore. And so we can prune that. And in this way, as the search space is explored, the branch and bound algorithm eliminates suboptimal solutions early by pruning and finds the globally optimal solution quickly. So in this case, the solution output would be this best known cost or the incumbent cost solution, that is A to C and D to B. At the level above, we are looking at how to optimally assign tasks to the fleet. So if we consider here a set of 12 different tasks, each with their parameters of pickup, drop off, cargo weight, and so on, we are looking at how to distribute it to the robot fleet that is available. And these costs are based on the route optimizing costs, which inform how each task assignment provides a certain benefit in the overall cost. To address this large-scale optimization problem, again, we use a branch and bound algorithm. Now, in this case, at every level, we're looking at which robot should be assigned to do that task. Now, some robots may not have sufficient payload capacity to be able to pick up that item. So that branch or that decision is eliminated there. Maybe a robot is unable to move fast enough to be able to do a pickup and delivery on time. So again, that branch does not exist. And we make these sequential decisions again, going from task level 1 to all the way to the bottommost level. Now, because this is a very large scale optimization problem, we split the search space across multiple processors, and we then share that pooled best solution cost among the processors so that they can improve their convergence rate by pruning suboptimal solution costs earlier. And in this manner, we reduce the computation time at this level. Now, the level above this, we're looking at how many of each kind of robot should be purchased. And in this case, the idea is to reduce the size of the fleet that's being considered early on. So instead of initializing with the largest possible fleet size, we start with a smaller candidate fleet. and then we solve the problem of task assignment and see what robots are actually being utilized in this fleet. And in this case, if we started with the robots as a maximum number 2 for each, but the utilized fleet has for omnidirectional robots the same number 2 as being utilized, we then increment the fleet at that level so that we can consider the possibility of maybe using one more of those robots. And we keep doing this until further additions no longer reduce the overall cost. And to make sure that we don't waste computational effort, we only compute task assignment cost when one of those additional robots has been is being utilized. So that is the exact algorithm. And as I mentioned, there's one more component, which is the hybrid algorithm aspect, where we use a meta heuristic to guide this search. To do this, we use Monte Carlo tree search, which is a state-of-the-art algorithm for solving large-scale combinatorial optimization problems. And here the MCTS algorithm makes decisions about the number of each type of robot to be purchased. So the steps that are executed involve selection. So in this case, we're starting out at the root where no decision has already been made. So we then expand to the possible decisions. In this case, maybe no, it could be 0 or 1 as a number of type 1 robots. So these two decisions we model here. And then we pick one and we do rollout of the remaining decisions. So that is randomly assigning the number of type 2, type 3, all the way to the number of robots. And then for the task assignment, again, we do a rollout. And for that particular solution, we then find the cost using a routing branch and bound. And that cost is then found for multiple such rollouts so that we can then find an estimate of that decision that's being considered, which is the average cost of all of these particular rollout solutions. So now that particular node has been assigned an average cost, and then we backpropagate this to all the levels above, which in this case is just the root node where the decision has been made. And then we do this again for the remaining node, which in this case is the selection of another choice for number of type 1 robots, and we backpropagate that as well. At this point, we can now make a selection at the next level, which is at number of type 1 robots. Do we choose the node on the left or the one on the right? To do this, there is a selection policy, which we call the lower confidence bound. And the idea is that we balance exploitation of solutions with very good cost, which in this case is a lower average cost, with the exploration of solutions that may not have been explored as much. So based on that, in this case, we select the node with the lower cost, and then we expand upon this, we continue expanding upon this, but we balance that exploitation of good solutions with the exploration of less explored solutions. So then we also explore solutions that might have a higher cost but have not been visited as often. And in this way, we continue to expand upon this search tree and find really good solutions early on. This is the advantage of the Monte Carlo tree search. And this meta-heuristic algorithm is then run simultaneously with the exact algorithm. As I mentioned, the exact algorithm has multiple processing cores assigned to it. We assign just one to the MCTS algorithm, but in doing so, the MCTS algorithm is able to find good fleet solutions early on, which could be used for the initialization of the exact algorithm, and also when fleet increments are being made, it can be used to inform what is a good candidate to be considered. Further, through the task assignment level, we are finding good solutions for how the task can be distributed between the robots, and that overall cost can also be added to that pool solution cost within the parallelized task assignment level. So all of this improves the convergence of the exact algorithm, and it does provide us optimality guarantees. So let us now look at some experiments. In this case, we look at 10 tasks with 3 types of robots, and what I show here is the exact algorithm running on its own without any guidance from the MCTS. We see the best cost is coming down, and it finds the optimal solution within 16 minutes. When we use the hybrid algorithm, we have 6 cores assigned to the exact algorithm and 1 core assigned to the MCTS. So we're trying to make sure that it is identical to the total computing power used by the standalone solution. And in this, we see that the guiding MCTS is able to find solutions early on. And in doing so, it improves the convergence of the guided exact algorithm. In this case, the hybrid algorithm, which is a combination of these two, it finds the optimal solution 87% faster than the standalone one. Similar behavior is also seen for larger cases where there are 20 tasks with 3 types of robots and 7 as the maximum number of each kind of robot. In this case, the guided solution is able to find the solution much quicker. So, in terms of an actual case study with some parameters that are informed from production facilities that are in the real world, let's consider this case where there is a production facility and there are 20 tasks that require movement of material, and there are 5 types of robots available. And at each task, there's also a set of parameters that define what is the weight to be carried and what are the time windows of drop off. We run this problem on the Ohio supercomputer using 28 cores for 3 days. And here is the output solution, which is the globally optimal fleet composition, which has these number of robots for each tank, and the fleet dispatch, which is how the robots go about completing their tasks and meeting their time windows and so on. So we see that for the 5 kinds of robots. In this case, the autonomous forklift is only completing 1 task. And this is based on the ability to distribute tasks between the other robots and respecting all the constraints. With that, let's move to the next research question, which is centralized fleet management, where the robot fleet has already been acquired, and now we're trying to coordinate between them. So in the nominal operation, the fleet policy is what finds how the tasks should be distributed between the robots, and it assigns routes to each robot. In reality, there might be slight changes in the parameters that define the material handling problem. For instance, the pickup location might be slightly shifted, or a robot's battery might have deteriorated and is no longer able to travel as fast or as long. And maybe a package has been dropped at some pathway which restricts movement. Now, a centralized fleet manager is responsible for reassigning tasks to the fleet robot and reassigning routes to each robot so that the material handling task can be done successfully. What happens here is that the problem parameters in this disturbed operation, it manifests as some perturbations. And this sets up a new problem that has to be solved, but this has to be solved in real time. And this problem is again an NP-hard combinatorial optimization problem. Because it's a very challenging problem, a lot of approaches in literature use meta-heuristic or deep learning methods, but these approaches do not guarantee some kind of algorithmic convergence. Decentralized fleet management systems are another approach where instead of trying to distribute tasks between all the robots, it only reassigns tasks to the affected robots or a subset of these fleet robots. This neglects the resilience offered by other robots in the fleet. Now, if you look at what actually happens, the new problem that is being solved is very similar to the original problem, just some parameters have been slightly changed. So, can we use the knowledge that we gained while solving that nominal operation problem for accelerating the convergence in the true operation? To do this, transfer learning is a systematic approach that utilizes the knowledge from that first optimization to accelerate convergence in a slightly shifted problem. Now, the approach of using transfer learning is to structure the information in a very systematic manner, but retaining all that search space knowledge is impossible because of the exponential growth of the problem search space with the number of variables. But Monte Carlo tree search is an algorithm that constructs the search tree with more information in the promising regions, and it explores the other regions as well. So to address this, we use Monte Carlo tree search to first solve the nominal problem, where the decisions that are being made is related to how the tasks are distributed between the. In this case, if we have 2 robots, we're making decisions about which robot gets to do what task. And here I show an outcome of running the MCTS for 12 hours with a task set of 25 tasks. What I show here is the average cost at every node and the number of nodes at that. Usually we end up with about 50,000 to 70,000 nodes in the MCTS search tree, which is a lot of knowledge about how these decisions are resulting in an average cost. To visualize how these decisions are related to each other, I show now with a radial representation for a certain task level, how the costs of the nodes are distributed within the range of the costs. And so as we go to a deeper node, which is task level 25, we would have a very large variation in the overall average cost, and that's what you see here. If you look at the relation between the different nodes, we can represent it using these edges. And you can see that there is a lot of exploration happening in this particular region. And for some decisions, we see a significantly reduced average cost. Now, this is a very important outcome because it's able to structure that knowledge about the search space very efficiently. But as MCTS is running for the nominal problem, it also optimizes the cost for task assignment, which in this case, we see that the cost is reducing. and we can, at the end of some computational budget, we can lowest cost as a nominal policy, which is how the tasks are assigned to the different robots. Alternatively, if you know what is a globally optimal solution, you can run the MCTS until that solution is found by the MCTS, and then you can. Now, all of that was for the nominal problem. When we have a perturb problem and some parameters have shifted, what we do is that we make use of the search tree topology, replicating the structure of the tree, but setting all the average cost to 0. And then we pick the lowest cost nodes from the nominal tree, and then we explore those particular solutions for the perturb problem. So in this case, we pick this particular node, which is a set of decisions about task assignment, and then we check that solution in the perturb problem. Once we get that solution cost, we then backpropagate those costs along all the decisions that related to that particular node. And we do this in increasing order of costs. And in doing so, we are looking at promising regions of the search space. And also, we are finding an update for how these costs relate to the new problem. And in doing so, the search tree is being updated simultaneously. Next, we use multicolored research after that budget of visiting these promising nodes. And we reinitialize MCTS now goes from top to the bottom, exploring previously unexplored solutions and also finding possibly new solutions that would not exist in the previous tree. Let's now look at some computational experiments. So here I show a relation between pickup and drop-off positions that have been defined based on the TSP library. So this is a benchmark set of point clouds which provide points for pickup, drop-off, and depot. And the idea is that these robots that form the fleet must now go and pick up these items, drop them off, while maintaining their battery capacity and so on. Here I show with the plot here the time on the x-axis and the optimality gap. So we have the truly optimal solution, so I'm able to show the optimality gap. And the centralized fleet management system, which does not use a transfer learning approach, is shown with black. You can see that the convergence plot is higher than the plot shown with red, which is the case with transfer. So you can see that the transfer learning approach is able to find solutions quicker. And here I show the case where the top 5th percentile of the nodes have been evaluated. And we're able to see a lot of improvement in the convergence at that point, after which the MCTS is reinitialized, and then we can see further improvement. The decentralized solution in this case does not reassign tasks between the robots, but instead just reroutes the robots to be able to find a feasible solution. Now you can see that the solution is found very quickly in the order of milliseconds, but that solution remains at a high optimality gap, while the centralized methods are able to improve upon the convergence. Now, to account for stochasticity involved in the rollout of the multicolored research, we solved the nominal problem 25 times, each with 12 hours of computation time. And we see here the solution cost reducing in a different convergence plot for each set. And because the nominal solution involves because there are multiple nominal trees involved in this solution, we see then that when we use the decentralized approach, we have multiple solutions that come up with that task assignment. Now, while the transfer learning approach is able to reduce optimality gap within a few seconds, the decentralized solution finds a cost very early on, and the transfer learning can reduce this cost given just a few seconds. As you can see, for 1 second and 1 minute, the transfer learning approach is able to find a much better distribution of the costs. Given enough time, as you can see, as the time approaches 2 or 3 hours, both the centralized algorithms have similar costs. We can look at some other perturbations where there is a battery deterioration instead of 20%, a case of 40% reduction. We see again the transfer learning approach is able to produce a better distribution of solutions. While when the payload capacity is reduced by 20%, we see similar behavior for 20% and for 40%. All of these parameters were just one parameter being affected. But if you now look at a case where there are multiple parameters being affected, in this case, where the locations of each of these points can vary within some box of uncertainty. You can see if you look at the pickup and drop-off locations, they have shifted. Now the cost to go between any two locations has been affected. So for 25 points, 25 squared number of parameters have been affected. In this case, we see again similar behavior, but when you have a larger range of parameter variation, the improvement from the transfer learning is not as pronounced. And so the effectiveness of this fleet management is dependent on the severity of the parameter perturbation, and there is an interest in understanding what is the largest possible perturbation that can be handled successfully by the fleet management system. This brings us to the next research question, which is defining the feasible operational envelope to quantify the resilience. So here we are looking at finding what are the largest possible parameter perturbations that can be successfully handled by the system. To illustrate this, I will use an example where again I have a benchmark instance from the Lee and Lin dataset where there are pickup and drop off locations that have been defined for 51 tasks. And so there are 103 locations, multiple parameters defining the commodity needs to be transported, time windows, and so on. And we're looking at how much of a shift can be handled successfully by the fleet. Now, this is a very large scale optimization problem for which there is no known optimal solution, but the best known solution distributes the tasks as shown here for 3 robots. They go and pick up and drop off the different items as shown in these routes. One possible idea of defining the feasible operational envelope is what is the largest variation in these X and Y parameters for which the routes remain feasible. And a simplistic way of doing this is to just assume that the fleet manager does nothing and we just want to find how much of a variation can be successfully handled. The cause of the perturbation is this variation in the parameters. So I'm going to show the results from the algorithm that I developed to motivate why this is important. So let's say that we are interested in this particular point. We then have this as a feasible range of variation for that point for which the routes remain feasible, which means the time windows are. The feasible operational envelope is the outer limit of this region, and it defines what is the classification of a point on the interior and exterior. Interior being feasible, exterior being infeasible. For different points, we have different areas of these feasible operational envelopes. So in this case, this point has only a much smaller region of range. So this means that the FOE area defines the resilience for that particular system when that parameter is being changed. Another component is the fragility, wherein the system, if you look at how far is the FOE boundary from that system parameter, then if it's a very small distance, then the system is fragile. Because if the perturbation is anything more than that small value, then the system fails. So there's a sense of fragility. To visualize this easier, instead of showing the very large areas, I use a star to show systems where to show parameters where the variation in that parameter is very it does not affect the system as much. So if the area is greater than 500, I use the star, and if it's less than 500, I show the area. So for these locations, we then have this set of points where the area is so large that we do not really have to worry too much about that parameter varying. While for these other locations, the parameter variations can be quite critical to the system feasibility. By looking at these area values at each parameter, we can then decide which among these points is most critical to the system, that is, which is most sensitive to parameter variations. So we can then assign resources for maintaining the quality or maintaining those parameters to be the same as the nominal problem. While for the least critical cases, we can reduce how much resources we allocate. So herein lies the motivation of defining this FOE. Now let's consider the case where there are 2 parameters being simultaneously affected. So the nominal point shown in this space is at the origin where there is no variation in the parameter, while some other point here is caused by a shift in the nominal parameter. So P is then updated to P plus psi. Next, there is an expected parameter variation limit defining the domain boundary. And there is some region for which that nominal parameter can vary and still the system remains feasible. So that is a safe region. And then there is the unsafe region where there is some failure in the system or some degraded performance. What we are interested in finding is this boundary, which I denote by partial S. Now, methods that address this localization sometimes use design of experiments where an expert defines what are the regions to be tested, but it suffers from designer bias and also it does not scale well for problems that are having multiple parameters. Automating this is active learning methods where hyperparameters are used to be able to automatically search the subspace to find decision boundaries, and it does so by querying at regions where it thinks is the boundary to identify what is the feasible operating boundary. But in doing so, because it is testing in these predicted areas, it results in wasted queries. Also, there is no method in literature that guarantees the localization accuracy, which is of interest to us if we want to be able to comment on the fragility of the system. Generally, the idea is to query a point in this space of parameter perturbations, and then some classifier function says if that query point results in a failure or if the system was able to successfully withstand that parameter perturbation or the disruption. In the production context, this means the fleet manager affects this classifier function. The fleet manager might be proprietary, which means we don't have access to the inner workings, or it could depend on the algorithm that's being used and so on. It's also dependent on the problem characteristics. For instance, is the parameter relaxed? The time windows are sufficiently large so that the robots can find feasible solutions? Is the distance too large that the robots are not able to travel as long in sufficient time? And there's also a budget issue where there could be multiple processing cores. Do we have access to a supercomputer or is it a single processing core? Is there a time limit for computing these feasibility solutions? And what is the permissible cost increase? The problem here is that if we try to explore the search space by randomly querying, there can be an issue where the function evaluations are expensive. And so we want to be efficient in our querying. Ideally, every point that is being evaluated should contribute to the localization of that FOD. Also, we're interested in guaranteeing that localization. So this partial S should be localized within some user-defined epsilon neighborhood where the epsilon is the desired accuracy of localization. So if it's a highly critical system, we would want a very low parameter epsilon. So an updated objective here is to accurately localize partial S for a black box classifier function, which can handle all those variations in the possible classifications within a user-defined epsilon neighborhood and with high sample efficiency. The methodology that we've developed, it starts with bisection, where we know for sure that the nominal point is within the feasible region, and we have to find one infeasible point that is unsafe, after which we can use bisection to then close in on the boundary within some epsilon tolerance. So when the distance between the point in the interior and the exterior is less than epsilon, we can then stop the bisection process. And that leads us to a decision boundary walk, where we start with the last 2 points found by bisection, and then we query the epsilon circle intersections. What this means is from the 2 points that have been found, we draw 2 circles, and then we look at the intersection of those 2 circles, epsilon radii circles, and we pick a particular point for querying. So to be consistent, we use a negative relative cross product between the intersection and the last 2 points. In this case, let's say the query resulted in an unsafe point being detected. Then next, we shift our circle centers to be the last point which is infeasible and last point which is infeasible. And now we look at the intersection again, query there, and now we shift the circle again, query at the next intersection, and in this way we keep exploring in such a way that the last 2 points are feasible and infeasible. By doing so, we are effectively localizing that partial S, the FOE, in such a way that the distance between the points is less than or equal to epsilon. So because of this aspect, we are basically localizing that partial S within the inner approximation of epsilon neighborhood and the outer approximation of epsilon. We call this algorithm the epsilon neighborhood division boundary governed estimation algorithm, and it localizes this this partial S within the epsilon neighborhood with high sample efficiency. So the system that we've been looking at was the Goldstein price function as a test problem. So there is a nominal point in the interior. We can test a corner to see if it is feasible or unfeasible. In this case, the corner is infeasible. And so we can then use bisection to find the localized partial S, from which we then run our algorithm. As you can see, it is able to travel very close to the FOE and also capture the nonlinearities associated. We see similar behavior for the Rosenbaum function as well, and also for the Beal function with highly nonlinear analysis. To note here is that the edge algorithm requires no hyperparameter tuning, and it only requires that user-defined epsilon neighborhood. And it's because of this reason, it is very well suited to diverse black box systems where we have no knowledge about how this FOE actually exists. Also, outside of the initial bisection points, every remaining query point contributed to the localization of that partial S with highly sample efficient. Now, another algorithm that does guarantee epsilon neighborhood localization is this naive approach where we sample through the entire search space And because we are searching with the grid cell size of epsilon by epsilon, we can be sure that the interior approximation and the exterior approximation do localize the partialness within that epsilon decomposes. But if we try to quantify the localization error, it would be quite similar to the edge algorithm, though the sample count is much higher. So this is an approach that uses that does provide epsilon neighborhood localization guarantees, but it is highly sample limited. Another approach that we've briefly discussed is the active learning at the boundaries, where we start out by randomly searching the search space of parameter deviations, and then we label those points and use that to train a support vector machine. Now this finds a predicted boundary region, and it is able to then sample along the boundary, along highly diverse and uncertain points, to then continuously improve the predicted boundary. In doing so, as you can see, there are a lot of queries that are occurring outside of the true boundary, but it does, given enough time, find that localization. If we limit the number of sample count to be the same as the edge algorithm, you can see that the accuracy is much lower. So the error is much higher. So in summary, the ALB algorithm has significant stochastic behavior because of that random initialization. It also requires hyperparameter tuning both in the support vector machine and also in how many points are used in the initialization and how many for learning what to count. For identical sample counts, we see that the computation time for the ALB is also much higher because the need for matrix inversions and so on. And across multiple test cases and repetitions, we find that the edge localization error is much lower. So in conclusion, the contributions I've made are related to developing a scalable algorithm that can compute the optimal fleet composition and dispatch for problem sizes that are relevant to manufacturing. And I enhance the ability of centralized fleet management using transfer learning to rapidly converge to much better solutions as compared to when we don't use transfer. Also, I developed Edge, which is a novel sample efficient algorithm that can localize the feasible operational envelope within some epsilon neighborhood guarantees. In terms of ongoing work, the application of edge to higher dimensions is something I'm working on right now. The idea is to apply edge on multiple cardinal planes and then use those points as wireframes for then making predictions for higher dimensional spaces. Also, the experimental validation of the centralized fleet management is currently being developed. It's a large team working on this. And the idea is to implement the centralized fleet manager and have humans create these disruptions so we cannot make predictions about how the disruptions affect the system. With that, I conclude my presentation. Thank you for your attention. And do you have any questions or comments?
Great. Thank you, Mithun. Now we open the floor for discussion. If oh, you don't say that. You click on that. It was not. All right. If you have any questions online, you can unmute yourself. You can type them into the chat, or anybody in the room with questions, please go ahead. Audrey, please.
So I know you said that you pre-calculate all of your routing information and your edge costs. Is there a way to incorporate things like intersections where the two robots might, in some cases, be running into each other? How would you anticipate that affecting your cost, and how would you have to change your hierarchical structure to incorporate that?
Great. Thank you for that question. That's a problem of conflict management, which is dependent on tracking exactly the time at which the robots are in a particular location and so on. Now, at the higher level of optimal fleet composition, that results in a significantly higher, much higher dimensional problem to solve. And so what we consider is that these problems might occur, but in reality, there are multiple routes that have similar costs. And so when these conflicts occur, we can either have a robot rerouted when this is detected, or we can have it that the robots maneuver around each other. So the maneuvering around each other is generally what is done in industry. So in Amazon robotics, robots travel along the same line segment, but then when they interact with each other, they move around each other and pass. And so we do not consider this to be sufficiently important to include in this very large scale optimization problem. That's right.
In the beginning, you mentioned that one of your constraints was when the robot leaves the depot, it has full charge.
Yes.
Did you consider like relaxing that constraint, say maybe like 90% of battery is okay, and seeing like how that affects
Yes, so
performance?
we did do a sensitivity analysis where, so what you described, we could also model as a change in the battery capacity that's available between 0.9 times what it should have. And so we have studied that, I think, quite significantly, especially because the solutions that we find are usually significantly optimized in the sense of managing the energy and so on. So now if the energy is, available energy is reduced, then the robot has to do charging events which significantly affects the time windows. So it does.
Okay.
Another question.
Yes, I have one more question. Were there, so because these are very like high level theoretical, and so I was wondering like specifically in the experiments you ran, were there any results that really surprised you just because how unintuitive are these solutions that you're getting?
I would say that this result here is kind of unintuitive because you would think so this particular result, it shows that there is one robot which is doing just one task, which seems like it should be suboptimal, but the reality is that all of the other robots are so fully utilized that they are only able to make the time windows just barely. And then this here is a robot with a lower acquisition cost, but unfortunately a high operating cost. And so they assigned it to just one task so that the operating cost remains low and it can find the globally optimal solution. But yes, it was counterintuitive when we found this as the solution, the algorithm converged within 3 days and this was done. It does heavily depend on the parameters.
You in the slide you show that there are 28 cores that you're using for 3 days. Like USC has more than that number of cores, so why not more and reduce the time a lot?
You're right. The reason why 28 core was used is because that is the so in that we don't have to use a different kind of parallel computing algorithm where we have cluster based distribution. So in this, the OSC cluster includes 28 cores. So I can just use that one cluster and then distribute between 28. Now, if I wanted to, I could have used all the cores and it would have been faster. But I just chose not to because
Would you achieve that?
I would not think so. Correct. I mean, so we did a sensitivity analysis where we increased the number of processing code. After a certain point, the improvement in the computation time reduces.
Like that's what I was thinking. Like, was that the reason?
That was not the reason, but it was because of the number of cores in one cluster. The different kind of programming that you need for multi-cluster parallel computing. Yes.
Just curiosity for the when you were doing the simulations with the deviations and say like pickup location, there's an accident or something blocking the path. The time to find the optimal solution was on the order of like thousands of seconds.
Yes.
So
In
which
about 6 hours.
okay, so which isn't is trying to it's not exactly real time. Like if that happened in the factory to find the optimal solution, it would take a while. Is it possible to reduce that?
So in the centralized fleet management, we are looking at addressing these problems in real time. And what we want to do is find really good solutions, but we don't necessarily need the optimal solution. Now, given enough time, this algorithm will find the optimal solution. And in the experimental work that we're doing, the idea is to allow it to continue to run until the next disruption happens. And at that point, the updated tree acts as the prior knowledge for the transfer learning again. So we can continue to keep using this algorithm within some rolling horizon tree.
Okay.
But yes, given enough time, it can find out.
So it's just like finding a better solution in a fast enough time and then using that.
Yeah.
Okay.
Usually these when there's an update that's happened to the parameter, now when you want to reassign the tasks, some of the tasks might already have been partially completed. And so one way of implementing this is that in the next cycle, we use this updated tasks. So that's what we're currently working on with experimental validation. In the next step, what we'll be doing is to reassign tasks in real within about a minute or so.
Okay.
But that would require state monitoring and so on.
Right. More questions from the audience? All right, give you